we're going to take a look here at a result called the squeeze theorem. Now you might also hear this referred to as the sandwich theorem. Now this is an important result because we're going to use it to prove two important trigonometric limits, and those limits we'll use later on to evaluate the derivative of the sine and cosine functions, which are really important functions to consider. So the theorem reads like this. If we're given three functions, h, f, and g, and they satisfy this inequality, so the h is less than or equal to f, which is less than or equal to g, for all x in an interval around a number c, except possibly at c itself. It doesn't matter what's happening at c because we're looking at a limit as x approaches c. And we also have that the limit as x approaches c of h is the limit as x approaches c of g equals L. So both limits of h and g are L as x approaches c. Then the limit of the f of x as x approaches c must be L as well. Now this makes sense if you think about it, because what we're saying is the h is approaching L as x approaches c, the g is approaching L as well, and the f is sandwiched in between them, so its limit is being squeezed towards the number L as well. Right, so it makes sense when you think about it. Now let's take a look at a graphic down here illustrating this. So down here we have the graph of three functions. We have the function g right here, its graph, the graph h down here, and then you see the graph of the f, the oscillating graph, is sandwiched between the two. And also notice that we have c down here on the x-axis and L over here on the y-axis, and for both g and h, as x approaches c, the g and the h are both approaching L right there. Alright, now the question is, what's happening to f as x approaches c from either side? Well, keep an eye on the dot right here. Let me back that up a little bit. Okay, so keep an eye on that value right there on the y-axis. That's the f of x right there. That's f of x. Right there. Now watch what happens to that dot as I let x slide towards c from either direction. It's going to settle down towards the L because the f is being squeezed between g and h. So you'll see what happens. Notice that that dot, as x gets closer to c, that dot is getting closer and closer to L, and then eventually it just settles down right on L. And the same thing from the other side. As x is approaching c, that black dot on the y-axis is settling down towards L. Okay. So that illustrates the squeeze theorem. Now let's take a look at a result down here, or an example. Let's show that the limit as x approaches 0 of x times the sine of 1 over x is equal to 0. Alright, so let's first of all note that the sine function satisfies this. The sine of 1 over x is always between 1 and negative 1. Alright. Now, if I take a number x and I multiply it by the sine of 1 over x, which is between negative 1 and 1, then certainly x times the sine of 1 over x is going to be less than or equal to the absolute value of x, because sine is between -1 and 1, and it's also going to be bigger than or equal to negative absolute value x. Right? That's true. So what I'm doing is I'm taking the number x, multiplying it by another number that's between -1 and 1, and then saying, well, the product is definitely going to be between negative absolute value x and positive absolute value and the absolute value of x. Okay. Now we prove this result below, but let's just go with it for right now, and we'll look at the proof in a second. Now from this inequality here, let's note that the limit as x approaches 0 of negative absolute value x equals 0, of course, and the limit as x approaches 0 of the absolute value x is 0. So, and the x times sine 1 over x is sandwiched between those two functions, and the limit of both of those functions as x approaches 0 is 0. Therefore, by the squeeze theorem, we have our result over here. Okay, so that proves it. All we had to do is find two functions that bounded the x times sine 1 over x. We found them to be negative absolute value x, positive absolute value x, and the limit of both of those were 0. So the limit of x sine 1 over x has to be 0 as well. Now here's a graphic illustrating this down here. So right here, the red curve is the graph of y equals absolute value x, right? That's the V-shaped curve right here. And the inverted V-shaped curve down here, the blue one, is y equals negative absolute value x. And the gold curve here is the graph of y equals x times the sine of 1 over x. And you notice the red and the blue curve, as x approaches 0 from either side, they're both approaching 0 on the y-axis. And because the x sine 1 over x is squeezed or sandwiched between them as x is approaching 0, these oscillations are getting forced down to 0 as well. Okay, so that illustrates why the limit of this function is 0 as x approaches 0. Now, down here is a more detailed proof of that inequality. Let's just look through it quickly here. So to prove this inequality that we reasoned earlier, just note first that the sine of 1 over x is always between -1 and 1, right? Also, if I look at x divided by absolute value x, that's always between -1 and 1 as well, right? A number divided by its absolute value is going to be between -1 and 1. Except for 0, of course, but we're not worried about 0 because we're looking at a limit as x approaches 0. And so if I multiply this number times sine 1 over x, both those numbers are between -1 and 1. So the product, the resulting product, right here, the product of those two numbers will also be between -1 and 1. Okay? Now all we have to do once we have this, is just multiply everything here by that absolute value x. Right? If we just multiply -1 times absolute value x, the middle term times absolute value x, and the 1 times absolute value x, we don't change the inequality because that's a positive number. We don't have to flip those signs, and we end up with the result that we want. Alright, so that's a proof of that result. Alright, so that concludes our discussion of the squeeze theorem.